All right, so I'm a little bit late today. It is already 5:32. So we're going to get started with the class. Do we have any questions from the previous class? No questions? All right. Well, I know that we only have about 2 days bef- you know, between this class and the one before, but I hope you guys got some time to review the material because this is where things get a little bit difficult to connect, okay? Because I'm trying to abstract a pattern. So every time I try to extract a pattern, it becomes kind of difficult because there's the notation, there's also the rationale behind how everything is connected. So some of you may need some extra time to absorb the material. And I would say typically this is where some people start to lose connection to the course content. So I'm just telling you guys ahead of time so that you can allocate enough time to absorb this material. All right. So without any questions, let me just kind of go back to the previous slide, okay, on my tablet. Give me a second so I can bring that into your view. All right. And by the way, the tool that I'm using is called SCRCPY. And can anyone guess, why it is called SCRCPY? Screen copy. Yep, that's it. And of course, anyone who is true to the Linux style of commands, you would say, but they misspelled your copy. It should be just CP, not CPY, because that's the actual command to copy a file in Linux or anything that is Unix. All right. So this is where we left off last time. Okay. So it's kind of nice when the professor also took his own notes, right? Okay. But I hope you guys took your own notes as well. And before I forget, I want to address one point about the exams. All the exams of this class are open book and open notes. You can bring any amount and from any source, any material that is on paper. And when I said paper, I meant dead trees. I do not mean e-paper, so no tablet, no electronics. They have to be on actual paper. So if you have been taking notes on an iPad or some a similar device, then you need to think about how you want to print the electronic notes. Okay? So you have to plan ahead of time so that by the time we have the exam, you would have everything in place already. Yes. Well, according to the syllabus, it is usually about one third through the semester that when we have our first exam. So the exact date depends on how quickly we cover the material. Usually it will be off by maybe a week or so, between semesters, depending on the pace of the class. Okay. So so your notes is going to be the basis of your study guide. I do not provide a study guide. The study guide is yours to produce, and typically you don't want to wait until a week before the exam to work on the study guide. You want to work on it as we go. Okay, so basically after each class, now each class is what, 80 minutes, so you're supposed to spend 160 minutes outside of the class, outside of the lab, to work on the material. I would just use about 20 to 30 minutes of that time to kind of jot down what is important, what you might think is important in an exam, and kind of determine the format that you want to use on the print on the paper that you will bring to the exam. There's no limit to the amount of paper, so there's no need to write really, really small to try to fit as much as possible onto one single sheet of paper. So you can bring as much as you want or nothing if you prefer that way too. All right, so I just want to remind people how that goes so that nobody is surprised by the time we get to the first exam. Yes. Nope. It can be printed, it can be written by hand, it can be a screenshot of the video recording. Sorry? As long as it's on paper, on pieces of paper. Yes. Yes. but only before the exam. I have to qualify everything, because obviously I have very smart students in the past, who go like, but you only said that everything on paper is okay, so I'm just passing this piece of paper to my friend who's sitting next to me during the exam. It is still on a piece of paper. So now I have to make it very clear that sharing has to be happening before the exam. All right. So, are there any questions about what we see on the whiteboard? Okay, so yes, a few more examples. Sure. Okay, so we'll do a few more examples. But the first thing I want to emphasize is the only thing of these pictures of the abstraction that is actually specific to base 10 is here and here. The constant of 10 does not appear anywhere else. I see Ilya is holding on to his cell phone. Yes, I'm walking out of the view as he takes a picture. Otherwise, I have to hack his cell phone and remove my facial image from all of his pictures. All right. So we are good with this. Okay. So let's go ahead and do an example, but not in base 10. Okay. Yeah. Base 10 is boring. So, since we are not using base 2, might as well choose some other bases. So I'm going to say that we are going to use base 7. Okay. Because I'm fond of heptapods. So we're going to use base 7. So we're going to have 5, 6, 2 plus, let's try 1, 3, 5. All right. So this is all in base 7. And I am going to also name the rows. Okay. So we have XY being the numbers being added. So XY are provided because they are the numbers being added. We have Q, which is kind of like a partial sum. I don't even know how to call that, but it is just kind of like a partial sum. We have K, which is the row of all the carries, and then we have S, which is the actual sum of the entire operation. So at this point, we can assume K0 to be a 0. So what is K0? Well, we number the columns. This is column 0, this is column 1, this is column 2, and this is column 3. So I'm just going to write the line under that so that it is clear that this is just for naming the position. So now we have x0, x1, x2 being 2, 6, and 5 respectively. We have y0, y1, and y2 being 5, 3, and 1 respectively. So is the nomenclature or the way things are named clear? Okay, so the letters go by rows and then the digits go by columns. Okay, so we'll figure out the entire Q row first. So how is Q of I defined? So it's a single digit sum of the respective X and Y digits. So the way it is calculated, okay, in base 7 is R of Q of I is R of xi, yi, which is also in this case xi plus yi, the whole thing mod whatever base we are using, which is 7 in this case. Okay, so we just have to work this out. What is 2 plus 5, the whole thing mod 7? 0. Very good. So we start with a 0 here, and then we now have a 0 over here. What about the first column? What is 6 plus 3, the whole thing mod 7? Yep. Okay. And 5 plus 1, the whole thing mod 7? All right. Excellent. Okay. So that's a pretty easy row to work out. Okay. So the R function is what I call a single digit sum function. Okay, I'm sure the mathematicians have a better way to name it, but that's how I name it in this class. The k column or the k row is a little bit more difficult because it is k of I plus 1 equals to c of xi yi plus c of qi ki. And then c of uv, okay, I'm using uv just as the name of the parameter here. So c of uv is what? If I'm dealing with base 7, what is c of uv? Yep, that is correct. So this was introduced on Tuesday. It is just a definition. So I am expecting you guys to know it already at this point, okay? Because this has to do with knowledge. There's no quote unquote understanding involved. Okay, you just remember, oh, okay, R of something is defined this way, R of, a C of something is defined this way. So you have to get the knowledge down first before you can even start to make association between pieces of knowledge. So I just want to kind of remind people, you really have to spend time to get used to the symbols and the definitions. Okay, so in base 7, I put a 7 here instead of a 10, and you can also see how the R and the C function are pretty much the same as what we talked about on Tuesday, except the 10 is now replaced by a 7. Is that okay? So none of this math should look complicated. Tedious? Yeah, kind of tedious. But complicated? Nope, it should not be complicated. So now we work out what is k of 1. Okay, so if you want to work out k of 1, which goes into this spot over here, what would that be? So don't think intuitively, think using just the definition that we have in place here. So it'll because it is 1 because it is c of x0, y0. So basically, we are looking at 2 plus 5. Is it greater than or equal to 7? The answer is yes. It returns a 1. And then we look at, well, if you want to, you can also look at c of q0, k0. In that case, it will be 0 plus 0, which is a 0. And we are asking whether 0 is greater than or equal to 7. The answer is no, which means it is a 0. So 1 plus 0 is a 1. So that is the conclusion of why this is a 1 right here. So now we can also try to answer the question of what is k of 2, which goes into that spot over there. So now you look at the definition, okay? So once again, I don't want you guys to use intuition to answer the question. Instead, use the equation and the definition of the functions. So we look at 6 plus 3, um, and then we say, is that greater than or equal to 7? The answer is yes. So C of x1, y1 is a 1. But then we also want to look at C of q1, k1. C of q1, k1 is 2 plus 1, which is a 3. 3 is greater than or equal to 7 is false, and therefore it is a 0. So that means we have 1 plus 0 again, which is also just a 1. So now we put another 1 here. And then we also want to figure out what is K3. So K3 is right here. So with K3, the pattern is a little bit different, or which one is a 1, which one is a 0 is a little bit different, because C of x2, y2, which is 5 plus 1 is greater than or equal to 7, is false. So that's why your C of x2, y2 is a 0. However, C of q2, k2 is 6 plus 1 being greater than or equal to 7, which is true, then it returns a 1. So now we have 0 plus 1, which is still a 1. So now we have another 1 over here. Is that process understood? Sort of. Okay. Yep. Go ahead. To be both ones. We'll explore that in just a little bit. Okay. That's an excellent question, and we have to address that question um, as we transition to binary. So remind me if I don't address it, after we finish this example. Yeah, go ahead. Because it depends, because this digit depends on what happens in the previous column. That's why it is ki plus 1 depending on xi, yi, qi, ki, because those are all referring to the values from a previous column or the column to its right hand side. Nope, the structure does not change. It does not depend on the base, does not, that's the way it should be. In fact, that's how you do your multi-digit addition. It's just that we normally do not write out the Q row. We just kind of mentally keep track of the Q row. And we normally also do not write a zero when there's a carry of zero. We just do not even write that tiny little one. So it's just a change of convention right now. Oops. Uh, my computer went to sleep, and it only happens when I'm in this classroom, which is kind of weird. Hmm. Nope. It just came back on my side, and this should come back shortly on the screen. Say again? Cap. Hmm. Oh, I can always turn off the screensaver. I think it's the power management of the screensaver that's causing the problem. Oh, okay. All right. So we're still recording. I'm just double checking that, make sure that it is still recording. Yep, we're still recording, so we're good. All right. And yes, I just apply this equation when I equals to 0, when I equals 1, and also when I equals 2. And then I just plug in all the values. I'll show you one. Yeah, I'll show you one particular one. So I can say when I equals to 0, k of 1 is c of x0, y0 plus c of q0, k0. And then when I equals 1, then we have k2 equals to c of x1, y1 plus c of q1, k1. And then because I already know the values of the respective digits by the time I get to when I need to calculate k1, I just put all the values in, use this function to evaluate each one, and perform all the calculations. It's just tedious. So is your question about the C function, or is your question about the addition? I really do not, I cannot tell. You just use the values, right? What is x0? Yes. And what is y0? Okay. What is q0? Because by the time we try to calculate k1, q0 is known already. What is q0? And what is k0? Yes. And what is c of 2 and 5? No. What is c of 2, 5? The definition is on screen. Even if you did not study, the definition is already on the screen. What is c of 2, 5? C of 2, 5 is 2 plus 5, the whole thing, being compared to 7. If it is greater than or equal to 7, we return a 1. Otherwise, we return a 0. So C of 2, 5 is 1. That's right. Yep. At this point, yes, that's what I said earlier. At this point of this class, K0 is assumed to be 0. Yep. Mm-hmm. Yes. Yes. You never get a carry of more than 1. You should not. So we'll address that question because what you're asking is can we possibly end up with a carry of 2? So we'll address that in just a little bit. All right. So the next equation is S of I is R of Q I K I. All right. So now that we have Q and K completely computed, let's figure out what is S0. S of 0 is 0 plus 0, the whole thing mod 7, which is still a 0. Okay. What is S of 1? It is 3 because it's 2 plus 1, the whole thing mod 7, which is still a 3. What about the next one, which is S of 2? That would be a 0 because 6 plus 1 is a 7. 7 mod 7 is a 0. So there we go. So we have just completed, a multi-digit addition in base 7. The only thing that we changed compared to what we talked about on Tuesday is this used to be a 10, now it is a 7. I'm not tall enough, but that 7 on the top used to be a 10, now it is a 7. Yep, the plus 1 up, yeah. So this is k of open bracket k I plus 1 close bracket. Yep. hmm So that we are basically saying the k digit of the column to the left-hand side depends on everything on this column. Yeah, we typically don't need to go -1, but it's just a relative, right? It's just saying that the 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 k bit that you need to calculate depends on the column to your um, right hand side. Yep. Huh? Well, let's see how we can interpret this value because this is in base 7. The whole thing is in base 7. So this is telling us that we have 0 of 1, 3 of 7, 0 of 7 squared, which is 49, and then we have 1 of 7 cubed, which is 343. So, okay, so let's double check, okay? So, if I were to ask you guys, can I double check whether this math works or not? What would be your answer? Exactly. Okay, convert x and y to base 10, perform all the calculations, and then go back and check the answer of the sum to see whether it makes sense or not. Let's do that, okay, because this is also good exercise for base conversion. So 562 in base 7 is 5 times 49 plus 6 times 7 plus 2 times 1. And my arithmetic is not always reliable, but I'll do my best. Okay, I think this is 195, and this is 42, and this is just 2. So now we have 237 plus 2, which is 239. Okay, that's just my math. 245. So where did I mess up? 5 times 49 is, you're right. Okay, 249, 245. Okay, so everything is off by 50. Okay, so the answer is 2. Yeah, okay, let me redo everything here. So it's 287 plus 2, which is 289. Okay, thank you. All right. So what about the other one? 135. 135 in base 7 is 1 times 49 plus 3 times 7 plus 5 times 1. So that's just 49 plus 21 plus 5. So that's 70. So that should be 75. Is that correct? Of course, I can use a calculator to do this, but I just want to. Yep. Okay, works good. Okay, so we'll add the numbers in base 10 first. So when we add these two, okay, we have 364. Okay, that seems correct. Okay, so now we go like, okay, what about the actual sum? We have 0 times 7, so that's a 0. 3 times 7, which is a 21. 0 times 49, which is a 0. And then we also have 1 of um, 7 times 7 cubed, which is 343, I think. Yep. Okay, something is off. I'm off by. Oh, no, no, no. It's all good. Because 343 contributed by this carry, overall carry, plus the 21 is 364, which is also what we got by adding the converted x and y in base 10. So everything checks out. Okay. Now, does that mean that I'm absolutely correct? Not entirely, but the chances of something has gone wrong is pretty low because I can make two mistakes and they quote unquote cancel out each other. Okay, that's possible, but very unlikely. So are we good so far? Okay. What about the process itself? How we applied the actual definition? So the definitions are here, but there's no need for you to copy from the projector because it is in the notes also. All of those things are defined in the notes. Yep. So when we write the answer, we just write 030 with an overall carry of 1. In other words, the number of digits of x and y and s, they should be the same. All right. All right. So I think I can re-emphasize the importance of studying and reading, the notes, okay? Because the definitions are important, okay? Without knowing the definitions in the first place, there is nothing to make connections of. And understanding is about making connections between things. So you have to know the things first. That's just knowledge. But once you understand how those things relate to each other, then you have understanding. All right. So shall we move on? Okay. So if I need to convert everything to base 2, what do I need to do? Can someone point out in on this particular screen and just tell me, oh, that's all you need to do? Yes. Not exactly. I'm asking about, if I need to perform base 2 multi-digit addition, what do I need to do? What do I need to do? What do I need to change on the screen? Yes, go ahead. Exactly. Okay, so let's do that. So on the next page, I'm going to look into um, base 2, base 2 addition. So we'll use, R of UV. So that would be just U plus V, the whole thing, this time mod 2. Because base 2 or binary means our base is 2. So we change the only two places that mentions the base from 7 to 2. And then the other one is carry. So C of UV is U plus V, the whole thing is greater than or equal to 2. And if so, return a 1, otherwise return a 0. I just remember I forgot to answer your question earlier, which is can both of the C function return a 1? Do you remember that question? Okay, so let me address that question first. I do apologize that I'm doing things a little bit out of order. So the question that somebody asked, what's your name? Robbie. So that Robbie asked was, can this C return a 1 and this C function also return a 1 at the same time? That was the question. So let's take a look at what is implied when one is returning a 1 and how that can may impact the other one. And this does not even depend on the base itself, so I can even generalize the discussion to any base. So I'm going to use the next page to talk about this. Okay, so we're going to say, um, so we are really asking C of xi, yi plus C of qi, ki. Can both of these be ones? Okay, can this be a one while this one is also a one? So we work on it one step at a time. Okay, so we say, what if C of xi, yi is a one? What does that imply? Well, I mean, there's only one thing that is implied by the equation itself. It means xi plus yi is greater than or equal to whatever base you choose to use. Okay, but there's one more thing that we also know as a given, because these are single digit functions, so we know ahead of time that xi, yi themselves can only be between 0 and b minus 1. Does that make sense? Okay, so we're going to write it down because these are very important constraints. So xi has to be greater than or equal to 0, but it also has to be less than b. Same thing for yi, because they are single digits. Okay, as a single digit in base whatever b is, the digit can only go from 0 all the way to b minus 1. And that's why in base 10, we only have 0 to 9 as single digits. The value of 10 requires 2 digits to represent in base 10. Is that okay so far? All right, so now we look at all of these things, and then we go like, what about q of I? If you combine all of this stuff here, okay, it implies what is the range of q of I? So now you have to remember, how do we calculate q of I? Q of I is not an independent variable. It depends on x, I, y, I. Q of I is computed by what? Q of I is xi plus yi, the whole thing, mod whatever the base is, which is b, because that's just the spelled out version of r of xi, yi. Okay, so now you look at this and go like, let's see. The most x of I can be is b minus 1. The most y of I can be is also just b minus 1. So now you have b minus 1, the whole thing times 2, and then you have to mod it again with b. So how bad can it be? Let me just write it out. Okay, so in the worst case, x of I is b minus 1 because that's the maximum value. And then in the worst case, y of I is also just b minus 1. So in the parentheses, in the worst case, you have 2 times b minus 2, the whole thing, mod b. So the question that I am asking you is, what is the largest value? What is this? Okay, assuming that xi, yi are all maxed out. What is this? Now, this is a little bit of an unfair question because they don't talk about these in algebra. So I will tell you this is just b minus 2. Okay, so when I say something like that, what are you going to do? I'm just going to jot it down and memorize it. No, no, don't do that. Okay. So one thing you can do is to substitute the b with an actual value. Okay. So let's just say that b is 5. We're dealing with base 5 numbers. Um, so xi can at the most be a 4. Yi can also be 4 at the most. 4 plus 4 is an 8. 8 mod 5 is 3. Oh, wait. If b is 5, 5 minus 2 is also 3. So is that a formal mathematical proof of what I just said? Nope, that is not a formal proof, but it does give you a sense of, okay, it seems to work out for base 5. Now you can try other bases, and you will see the pattern does not change. Is that okay? Why is that important? Well, that is important because the second portion is C of Qi Ki. So now we look at C of Qi Ki. C of Qi Ki is Qi plus Ki, and if the whole thing is greater than or equal to the base, then we return the zero, we return the one, otherwise we return the zero. That's how it is defined. So now you say, well, Q of I can at the most be B minus 2. K of I can be at the most 1. Okay, now I'm not going to say why we can assume K of I to be a 1, because that depends on proof by induction, because the first column is guaranteed to have K of 0 being a 1. No, K of 1, how should I put it? Uh, we can assume K of 0 to be always between 0 and 1, and by proof of induction, we can now use that as an assumption. So if K of I can only be a 1, Q of I can at the most be B minus 2. So when you look at this sum here, the worst it can be is, okay, so let's do this again. This is B minus 2. This is 1. So when you add those two, what do you get? B minus 1. Can B minus 1 be greater than or equal to B? Nope. So now we have just proven that if C of xiyi is a 1, then C of qi cannot be a 1. It has to be a 0. But that's only going in one direction. We also have to go in the opposite direction. So do you guys want me to see, do you want to see the proof in the opposite direction, or at least the rationale? Okay, so let's do that. So to go the other direction, we are now saying C of qi is a 1. So now we have to look at what this is implying. Well, k of I can only be a 0 or a 1. Okay, so that's a constraint, that we can assume for k0, and then by proof of induction, we can now prove all of the other ones. But for the time being, all we need to know is k of I can only be a 0 or 1. So that means q of I plus k of I is greater than or equal to b. And because we know that k of I can only be up to 1, so this automatically implies q of I has to be exactly b minus 1. Does that make sense? If c of qi is a 1, then we know the q of I has to be b minus 1. Yes? Hmm? Nope, qi has to be b minus 1, not 0. Huh? If b is 2, then q of I has to be 1, because b is 2. 2 minus 1 is 1. Yep. Yep. No, no, no. Okay. So, okay, we did not. This is a conclusion. Q of I can be at the worst b minus 2 only if c of xiyi is a 1. Otherwise, otherwise that restriction does not apply. Exactly. So now we go back to this side, okay? So if we know the q of I is b minus 1, then we also know, okay, another imply, we also know that xi plus yi, the whole thing mod b, is b minus 1, because that is how q of I is defined. Q of I is xi plus yi, the whole thing mod b, okay? On top, we also have one more restriction, which is xi has to be at the most b minus 1, and then xi can also be at the most b minus 1. So combined with those two restrictions, Now we guarantee that there's no way we can have a carry when we add xi, yi. Okay, let me expand that a little bit more. Okay, so we have this conclusion. We still have this restriction. This is a universal restriction. We cannot bypass this restriction here. This is why, by the way. So if we know that xi plus yi mod b is b minus 1, we also know that xi is between 0 and b minus 1, is also between 0 and b minus 1 inclusively, then the only conclusion you can make is xi plus yi cannot be greater than or equal to b. Does that follow or not? Okay, it follows for some people. So how do we prove that? That's one way to do it. You can also prove by contradiction. You basically say, let's just say that it does, okay? And then it will lead to a contradiction. That's proof by contradiction. But since this is not CISP 440, I'm not going to spend too much time on the actual proof itself. But to some people, this is already intuitive. By the time we get here, they're already convinced that if C of QIKI is a 1, there's no way C of XIYI can also be a 1. Okay, so now that we have, so that's basically a very kind of loose proof of why only up to one of the C functions can return a 1. You can have two zeros, plenty of opportunities for that to happen. But when you have a 1, only one of them can be a 1. Is that okay? All right. And why do you think, I put in this kind of time to talk about a proof, when this class is really about computer architecture and not about, mathematical proofs. Yep, that's one. And two, yes, because computer science is math. And three, because it is good training for you to start to think in an analytical way and also to practice your critical thinking. Okay, critical thinking means you're always asking questions. Okay, like what you just did. It's like, wait, can both of these be ones? That's a good question to ask. Okay, and then analytical thinking is how we break down the question and then go like, okay, so how do we analyze whether they can both be ones or not? What happens when this side is a one? What's going to happen to the other side? And if the other side is a one, what's going to happen to the first, to the left-hand side? So that's the kind of thinking that you need in order to succeed in computer science. If you choose computer science or anything related to computer science as a career. Now that if that turns out to be wrong and somebody gets a job and go like, I do not need any analytical skills or critical thinking skills, well, come back and make fun of me. I'm okay with that. I'm completely okay with that. I'll just be happy for you. Alrighty. So now we go back to base 2. So in base 2, we have R of uv being defined as u plus v, the whole thing, mod 2. That's R. And then C is, hmm? Yeah, I think that's the way it is defined. This is u plus v, the whole thing, greater than or equal to 2. If so, return to 1. Otherwise, return to 0. So this time, we're going to use a kind of interesting approach to look at the u and v as functions. So we're going to use a table. We're going to enumerate all the possible ways to feed into u and v, and then we look at all the possible answers. So now we go like, okay, this is u, this is v, this is r of uv in base 2. Okay, so let's see what's going to happen here. And I don't think you have to copy this because I believe this is also in the notes. Ah, it fell asleep again, and it's going to take a while for it to come back. Okay. System D inhibit. I can understand if my students also went into suspend mode in my class. You would think that I'm kidding, but my own child, one of my children, took this class when I was teaching it, and she fell asleep in every single class. My other kid, when he was taking this class, he was late every single class. Hmm? Yep, yep. But not it's not because of any special consideration. I was amazed as much as it's like, how did you pass the class? You know, and they didn't even ask me questions when we were home. It's not like I gave them like special instructions or anything like that. You know, when they were home, I just asked, so you were kind of late for school today, wasn't you? Wasn't you? And then my son would go like, yeah, but I had to finish my coffee. If I'm gonna be 5 minutes late, I might as well be late and enjoy my coffee entirely. Yeah, it's solid, man. It is so solid. Yep, yep. And then my daughter, my son took the day class, and then my daughter took the night class, where you guys are, and she's always falling asleep in the class. So by the time we get to the lab, she'll be, but she enjoys the lab, and she's never frantic, when she's doing the lab, because the way she learns is different. She learns by doing. So the lab is perfect for her because everything is kind of like, there's something to do, commands to type, logic sim stuff to put together, and you can actually see the zeros and ones, happening, and she learns really quick that way. But when we're in a class, I'm just talking about stuff that is in theory, she just falls asleep. So different people learn differently, huh? My entire household has very poor sleep hygiene, and that's including me, probably because of me. All right, and I have lost track of what I was supposed to do. Sorry. Oh, right. Okay. So no. Oh, okay. I remember now. I wanted to show you where to find it in the notes. That's it. So base two addition. So we got all the tables here already. So we got this, and then we got this too. So you don't have to copy anything because it's already in the notes. And of course, those of you who have read the notes already go like, "Yep, I know that." All right. So, but I'm gonna work on this, independently, just so that so that you guys know how it is done. Okay, that's it, right? Because U is a single digit in base two, it can only be a zero or one, and same thing with V. So this is. Does it look like a truth table? That looks like a truth table. Okay, but let's just kind of figure out what this is going to do. Okay, what is R of zero zero? That's an easy one. Okay, what about R of 0 1? R of 1 0? R of 1 1? That's the okay. So we almost got the truth table of OR, but not quite. Okay, so now we look at C. So C is kind of the same deal. All right. Okay, and this is B. Okay, 0 0 0 1 1 0 1 1. All right. So can someone tell me what is C of 0 0? C of 0 1, C of 0 1 0, C of 1 1. Okay, all right. So we'll take care of C first, okay? Does that truth table remind you of something? Conjunction and. Okay, very good. So that means ha, we can just use regular logical and to come up with the result of the C function because a regular logical and will give us exactly the same thing. Whew, cool. What about this one over here? What about R of UV? It looks like an OR, but not quite. Yep, it is exclusive OR. Okay, so that means So that means we can now say, oh, this is the same thing as U exclusive OR with V. That is the symbol for exclusive OR. So that exclusive OR will give you exactly the same four values. And then someone is going to complain and go like, but Tack, we have never talked about the logic gate of exclusive OR, so we cannot use it here. So that means it's not working. Fine, let's not use exclusive OR. What about this one here? Not U and V, or V, U and not V. That will give you exactly the same result as exclusive OR. Happier now? Okay? The whole point is to boil everything down to logical not, logical and, logical or, logical and. Why? Why are we boiling? Why am I trying to boil everything down to just logical operations? Exactly. Okay, because everything that can be expressed as a logical not, logical and, or logical or, we know how to work those out using transistors. To be more specific, we know how to use NAND gates to emulate all of those logical operations. And then on top of that, we also know how to use four transistors to implement NAND as a gate. Is that okay? So are we making that connection all the way from the first lecture when we talked about the NAND gate, using two P and two N type transistors, all the way up to here? Well, we're almost there, okay? Because there's one more thing that we need to do, which is the annoying plus, okay? Because remember, k of I plus 1 is c of xi yi plus c of qi ki. So this plus here is still an arithmetic operation. However, thanks to the question that you asked, okay, we now know that out of c of so out of c of xi yi and c of qi ki, there are only three possible choices here. They can both be zeros, okay. This one can be a one, then this one has to be a zero. If this one is a one, that one has to be a zero, but one and one never happens. Okay? So that means if I look at this and then I say C of xi, yi, or C of qi, ki, okay. Then we have 0, 1, 1. Okay, okay, that's kind of what we know. And then when we have something like this, okay, I'm just going to say this goes here, but this time we have a regular arithmetic addition. What do we get? Same thing, exactly the same, because the roll when both of them are ones is not going to happen. So in this special circumstance, we can use a logical OR in place of the arithmetic addition. So now we are complete. Okay, we are done because I just converted everything in multi-digit addition into logical operations. There's no arithmetic operations left over. Is that okay? Yep, go ahead. Yes. So subtraction is will the same module also covers the subtraction. So with subtraction, the rules are slightly different. So instead of carrying, we have borrow, right? And we still have a single digit, but not a sum, but a difference. But as it turns out, it is also quite easy to do everything using logic gates. So we'll talk about that after we are done with binary addition. Go ahead, you're next. To Okay, so just to do the carry, you need two AND because one AND for the XIYI, one AND for the QIKI, and then an OR to combine the results of the AND into the K of the next column. Yep. Divide using logic gates. So division is based on subtraction. So if you have subtraction, then we also have the ability to compare. And once we have compare and subtraction, we can do division. Addition is based on shifting and adding. So shifting is easy. Okay, in the worst case, if you say, oh, you cannot add, you cannot shift, fine. We'll just add a value to itself, and therefore left shifting, right? So and then you just have to add the rows of the same value shifted by different amounts, and it boils down to addition. So the bottom line is once we have addition and subtraction, we can then use those two to implement division and multiplication. Is that okay so far? Kind of. Okay. Let me take a look at the time. It's only 6:30. Wow. Okay. So now we can move on and talk about, we can do some examples. Okay, I know you guys kind of want to do some examples. So we'll do some base 2 addition examples and see whether we can get a hang of this. Okay, so we'll do a 1, 0, 1, 1 plus 0, 0, 1, 1 here. Okay, these are base 2. So we have X, Y, Q, K, and S as columns. So this time I am going to do this using the logic gate perspective. Okay, the first thing is K0 is given to be a 0. So now I can actually carry out the entire calculation. The Q is exclusive OR, which means if both are ones, then the result is a 0. If both are zeros, then the result is also a 0. If one is a 1 and one is a 0, doesn't matter who is who, then we have a 1. So that means we have a 0 here, a 0 here, a 0 here, and a 1 here. Is that okay? I'm not even adding and modding anymore. I'm just performing exclusive OR. Okay. So the K is now looking at X and Y or Q and K. Okay. So in this case, we have 1 and 1, which is already a 1. This is 0 and 0, which is a 0. 1 or 0 is a 1. So we put a 1 over here. Over here, same deal. Okay, 1 and 1 is a 1 already. 0 and 1 is a 0. And then this 1 is ORed with this 0 over here. And so we have another 1 over here. And then we have 0 and 0, which is a 0. 0 and 1 is also a 0. 0 or 0 is still a 0 over here. And now for the last K, which is K4 in this case, we have 1 and 0, which is a 0. 1 and 0 is also a 0. 0 or 0 is a 0. We put the 0 over here. And then the S bit is the R result between the K and the Q. But since R is now boiling down to exclusive OR, so now we are saying what is 0 exclusive OR with 0? It is a 0. 0 exclusive OR with 1 is a 1. 0 exclusive OR with 1 is a 1. 1 exclusive OR with 0 is also a 1. Okay. So we can use the same trick as last time to double check to see if the math is correct. In other words, we look at x and go like, okay, what is x in base 10? Because we know how to do base 10 addition kind of more intrinsically. So this one, x is, okay, 1011, which is 8 plus nothing plus 2 plus 1, which is 11. Is that okay? All right. Does everybody understand how I get all those powers of 2 and why one of them turns out to be a 0? You're good? Okay. All right. What about y? Y is 0, 0, 1, 1. So we have none of 8, none of 4. We have 1, 2. We have 1, 1. So that is representing 3 in decimal. When you add those two, 11 plus 3 is 14. Okay, so now we have to look at the sum. The sum is 1110. So sum is 1110. Okay, these are all in base 2. So that's 8. There's one of 8, one of 4, one of 2, none of 0, none of 1. So now we have 14. So the base 10 version adds up to 14. The sum of the binary addition also um, converts to 14 in base 10. So, well, I mean, once again, this is not a formal proof, but it is an example of how it works. So are we doing okay so far with this? Okay. Yes. The logic gate approach only works in base 2. So when you write a C program and you enter like a base 10 number, and then you say, okay, I want to get the sum between this variable and this variable, the moment it compiles, that constant that was specified in base 10 is first converted into base 2 before it is used to initialize the variable. So there's a conversion that is hidden away from you. Yeah. So when you see out the content of a variable, the variable is storing the value in base 2 intrinsically. So when you do a see out without any flags to tell it to convert to any other base, see out, the output function of see out automatically understands, oh, you want the output to be in base 10, so it actually has to spend some time to convert the internal base 2 representation back into a base 10 representation before it is presented to standard output. Yes, it's not so much the processor. This is all in the C standard library. It's software doing the conversion, not the hardware. Yep. So I have to be careful of what I say because the hardware is performing the addition in base 2. It's storing the result of the sum in base 2 as well. So inside, for computational purposes, everything is in base 2. It's only in the input and the output that the compiler on one end, would do the base conversion for you. And then on the other side, when you do a C out, with the symbol, that is also the C library doing the base conversion. So that the number shows up as a base 10 number. That is correct. So the processor does everything in base 2. The memory bank, stores everything in base 2. It is only when you're inputting and outputting, because we do not do base 2 very well. So that's why, the libraries, and also the compiler or the tools will automatically convert the base for us. Is that making sense? It seems like it can deal with base 10, but those are all, based on software. Uh-huh. I see. Okay, go ahead. Uh, I'm not sure which one because C++ has its own standard libraries, which probably reference CLib. Yep. Um, there's a choice. When you link, the loader or the linker, it can either link statically or it can link dynamically. So to the rest of the class, what that means is dynamically linked means, your code is smaller, your executable is smaller because you're counting on the operating system providing a runtime library to at runtime, you know, um, you know, resolve, oh, what is C out? Okay, C out is over here. What is string copy? String copy is over here. Statically linked means, the library contains little chunks of code that actually gets incorporated into the executable that you are creating when you're linking the program. So once you have that executable, which actually self contains everything that is needed, then it doesn't care about the runtime library version of the operating system. So that's kind of the difference between statically linked versus dynamically linked. One is more portable, meaning that, oh, you just get executable regardless of your version of runtime libraries. It will still run exactly the same way. That would be the statically linked version. But then the executable gets bigger because now you have to include all the snippets of all the functions that you referenced in your code. Dynamically linked will create a smaller executable, but now, if there are differences between versions of the dynamically linked library, then you're at the mercy of which version is actually installed in the operating system that your executable is running in. So if you don't understand a single word, that's okay. Okay, this is not, by the time you get to a compiler class, then you will understand everything. But if you already understand everything that I'm talking about, good for you. Um, But Python is not even a compiled programming language, so everything is kind of interpreted, when it runs. Yep. You can compile to C and then from C compile to. Yep. You can, but most people don't, because that kind of defeats the advantage of a scripting language. Mm, I see. Okay. But getting back to, doing performing addition in base 2, are we doing okay with this? Okay. We're good. All right, so we'll talk about subtraction. And trust me, subtraction is easy. So we'll do some subtraction in base 10 first, and then we'll do some subtraction in some other bases. So we'll do, let's say, 170, and then we'll subtract from it. We'll put a 2 here. We'll put another, let's see, we'll do a 2 from 3 from here, and then we'll do a 4 from here. There we go. So we have X, we have Y, we have Q, and this time we have a borrow, but the borrow is not a borrow. I will use a T here because B is the name of the function that I'm going to define later. So T is take away something, so that's why it's T. I know it's kind of lame, but I cannot use B. I have to use something else. Okay, so Q is the single digit difference when you're subtracting. So 0 minus 2 is, what do you think is the single digit difference of 0 minus 2? It's 8. Yep, it is 8. Okay, it is 8, a 1. Yep, but we'll get to that. 7 minus 3 as a single digit difference is, and then 1 minus 4, what is the single digit difference? No, it is 7. Okay, so what is the single digit difference? So I'm going to confusingly use R again to express what is a single digit difference. There's a reason why I reuse the symbol R instead of something else, okay? Even though in different bases, um, in anything other than base 2, R is, different from depending on whether it is addition or subtraction. Okay, so how can I define that? So one way to do that is just to say, okay, let's just add 10 to U first before we subtract V from it. And when this is all done, we're going to mod it with the base again, which is base 10 in this case. In other words, I am making sure. Oh, okay, I can see that you guys cannot see because some stuff is behind the clock. There we go. Okay, so the whole point is when I add 10 to U, I just made sure that there's enough quantity to perform the subtraction without going negative. Does that make sense? Because U is a single digit, which means it can only go from 0 to 9. And V is also a single digit. It can only go from 0 to 9. So if I add 10 to U first, then it is guaranteed to be at least 10. So that means the difference cannot go negative. But it can be a little bit too big, okay? Because if U is a 1 and V is a 0, then we have 11 minus 0, which is 11. 11 cannot be a single digit in base 10, so that's an easy problem to fix. Just mod it with 10, and we are now done. Is that okay? All right. And the borrow function is even easier. In other words, when we subtract V from U, do we need to borrow? Okay. So that's an easy one because all it needs to know is whether U is less than V. If that is the case, yes, we have a borrow. Otherwise, we do not have a borrow. So the B function does not even need to know what base we are dealing with, because if the single digit U is less than the single digit V, yes, we have to borrow. Huh? V is a parameter. Huh? B? Yes, B is for borrow. Yep. So now we have to define a few things. So now once again, we define Q of I to be R of Xi, Yi, but this time R is representing single digit difference. Um, T of I plus 1 is now B of Xi, Yi plus B of Qi, Ti. You go like, didn't we see something like this before? Except last time the B was C and then T was K, but the structure was the same. I hope you guys will recognize that particular pattern, okay? Because it is kind of related, okay? Addition and subtraction are very closely related. And then S of I is defined as the R of Qi, Ki. You go like, wait, that looks very, very similar. Okay, we don't have S of I, sorry, I take it back. We don't have K either. Okay, so that's my bad because I took everything from the addition. So we have this is D of I difference, and this is T of I for take. Well, but the mistake turns out to be educational. It was a learning moment because I just illustrated how closely related addition and subtraction are. I hope you guys notice the difference too. Okay, just switching a few letters. Okay, B becomes C, T becomes K, and D becomes S. It looks exactly the same as what we had. Okay, but the definition of R is a little bit different. The definition of B is also a little bit different. So with that said, okay, now we can go ahead and complete this calculation. There's always a zero assumed here. So when we apply t of I plus 1, okay, when we apply this t of I plus 1 here to compute t of 1, that means we have to look at b of x0, y0 plus b of q0, t0. b of x0, y0 is a 1, b of q0, t0 is a 0, 1 plus 0 is a 1. So we put a 1 over here. And then when we have to compute t of 2, then we are looking at b of 7, 3 plus b of 4, 1, and that is just a 0 over here. And finally, when we look at t of 3, we are looking at b of 1, 4, which is a 1, plus b of 7, 0, which is a 0. 1 plus 0 is once again a 1. And now when we get to D, we just say, oh, it is the single digit difference between the Q and the T. So 8 minus 0 has a single digit difference of 8. 4 minus 1 has a single digit difference of 3. 7 minus 0 has a single digit difference of 7. So the answer here is 170. Remember, these are all in base 10. So 170 minus 432 is 738. You go like, no, that is so wrong. It's supposed to be negative. Well, but wait. There's a little bit more here. We have an overall borrow of one. Then you go like, how is that one possibly going to negate, turn this whole thing into negative? Well, it is one, but it is one of what? What position is it on? It's a digit three, which means it is one of 1,000. It's one of 10 to the power of 3. We owe 1,000. Okay, so this means we have 738 bucks in our pocket as cash, but you are owing the bank 1,000 bucks. So what is your net worth? Yep, which is okay. Let's do some calculations here. So this is what you have. This is how much you owe, and doing the um, hmm, 272. Yep. Oh, the other way around is 262, not 70, because of the borrow. Yep. So now we double check. Okay. So now we actually do the normal calculation of this. Okay. 0 minus 2 is an 8 with a borrow of 1. 7 minus 3, then minus 1 is a 3. And then 1 minus 4 is a 7. Um, oh, okay. This time I actually have to use a negative. Wait. It is not. I'm doing the calculation wrong somewhere. Oh, okay. We reverse this and then we flip the sign. There we go. So 3 minus 7 is a 6, it's a 2, and then we just negate it. So this amount and this amount are the same. So are we understanding how to read this calculation? The subtraction ends up with a non-negative value, but the overall borrow is what you owe. And how much you owe, the magnitude of how much you owe depends on which column that overall borrow bit is. So in this case, because the overall borrow bit is on digit three, that means whenever you owe 1,000. Okay. All right. So we are ready for the lab. Let me give you the lab instruction so that you guys can go ahead and get started. All right. So the lab that you're doing today is it's just called addition. Unlock it, and I need to give you the access code. And this one it was built a little bit differently, so I have to get to the access code a little differently too. So we go to settings, and then we go to show access code. It is XYQKS all in lowercase. So if people are asking why did you use this kind of random bunch of letters, then my answer is easy. You might need to study a little bit more and pay attention in class. Do at least one of those two. Oh, well, thank you. All right, well, thank you. It is also a little bit harder, to most people. Hmm. Yeah.